Alrighty, guys. So we've already talked a lot about molarity. Okay, we've talked about how um, concentrated things can be, how we can dilute them, and we probably need a little bit more practice on calculating dilutions. But in the interest of time, we can always do more practice problems. What we can't do is we can't just like sit around and do nothing. So we're going to move on to something that molarity really depends on in the real world. Now, I live in the Midwest. A lot of you guys do. All of my students do. Um, but a big thing in the Midwest is, well, really anywhere they get snow is salt. Okay, um, salt is huge, huge in the Midwest. Okay, and I'm not talking about your table salt. I'm talking about road salt. Okay, we would not survive a winter without any road salt. Now, why do we really need road salt? Eventually, we are going to get to the point where we talk about why road salt is such a good thing for winters and why road salt uh, gets rid of ice. But first, we need to talk about what salts do when they get into solution. Okay, so salts. Let's say we've got our table salt, Na and Cl. Okay, we've got table salt, sodium chloride, NaCl. We've got some sodium atoms. 1, 2, 3, 4. There we go. And I'm not exactly sure what form the crystal structure takes, but we're going to assume it's like this. Okay. This is just a couple cubes, say, a couple grains of sodium chloride. Now, that gets added to water, H2O. Okay. We have to recall our thoughts on polarity. So H2O looks like this when it is drawn out into its Lewis structure. Okay, we have the hydrogens on the bottom. It is in a bent shape because of these two lone pairs right there. Okay, so those two lone pairs bend the hydrogens down, and we have a polar molecule because of this. Okay, we have a slightly positive side and we have a slightly negative side. Now, when these two things interact, you get water's negative side going and not attaching but attracting the positively charged sodium atoms. Okay, and then you have the other side, the slightly positive side of water, going and attracting the slightly negative or the negative chlorine atoms. That eventually, with all of the millions and millions and bajillions of water particles, eventually all of the individual atoms here will be separated from each other and surrounded, by water molecules. Okay, There's a couple good like animations that you can go watch on online that really show exactly what's happening when salt dissolves. It really gives you some actual physical way to see what's going on in water. But essentially, we get things broken up into Na plus and Cl minus. This is a big thing called dissolution. It's different from dissolving. Okay, this is not equal to dissolving. Okay, it's not the same thing. So dissolution is when things break up into charged particles. So we see that sodium and chlorine break up into their charged atoms, and they dissolute. Is that the word? Dissolute? I keep wanting to say dissolve, but that's not the right word. I just said that. You want to say dissolve because that's what you've been using for your entire life, but it is not. They dissolute. We're gonna go with that. It's probably wrong, but dissolute. So they break up into sodium plus, Cl minus, and they are probably almost 100% diluted. It sounds so wrong. Whatever. We're gonna go with it. 100% diluted. Okay. So, what happens when that goes on? Well, those dissolutions, those ions, they affect the properties of water. Okay. Now, normally you guys have already heard about water being like, you don't want to be in water when a thunderstorm hits, or you don't want to be in water and drop any electronics in, right? It's dangerous. And that is 100% true. And part of that reason is that normal water contains these types of ions in them. These ions allow for electricity to be conducted. Now, I'm not going to sit here and say that just pure water wouldn't do the same, but it's definitely not the same strength of conductivity. These little deltas that I drew over here on the water molecule, those are partial charges. They are not full charges. These on sodium and chlorine are full charges. So do with that what you will, but it means that they can conduct electricity much more effectively. We call them electrolytes. Okay, now something like sodium chloride would be a strong electrolyte. Okay, a strong electrolyte is something that dissolutes completely or almost completely, 100% some might say, so that there's no NaCl left over. It is all Na plus and Cl minus. Okay, something like sugar, strong electrolyte, we'll put NaCl there. Okay, a weak electrolyte would be something like sugar or glucose. Okay, now you can try it yourself. Go grab a glass of water, grab some sugar that's in your cabinet, mix them. What happens? They dissolve. Okay, it dissolves, it does not dissolute. Okay, sugar is made up of carbons, oxygens, and hydrogens. There's no there is no positive or negative charged atoms. Okay? There's no positively charged or negatively charged atoms. So these carbon and oxygens and carbons and carbon and hydrogen bonds, they do not break up very easily. Okay? Not as easily as the NaCl does. And definitely not in water. So they can dissolve, meaning they'll break apart from each other, but it is still an intact glucose molecule. Okay, it doesn't break up into its components like Na and Cl. Okay, we call that, why is that not erasing? Come on. Whatever. There it goes. We call this a weak electrolyte. Okay, it would not conduct electricity very well. Okay, so I'm going to give you guys some examples of different electrolytes. I want you guys to tell me, maybe, or think about it, not tell me, this is a video. Think about it before you hear my answer and say, is this a strong or a weak electrolyte? Okay, we got CaCl2. Strong or weak? Do some Dora stuff here. Is it strong or weak? We would say this is most likely a strong electrolyte. Okay, it is a metal and a non-metal, and it is with a chlorine, so it is most likely soluble. Okay, soluble. We got to review what that means again. Soluble is a solid that can dissolute in water. Okay, something that will break up into ions in water. Okay, we have solubility rules. If you do not, I would recommend going out on the interwebs and just typing in solubility rules. Very simple. There's a ton of them out there, and you guys can follow those rules to determine whether or not a compound would be soluble in water. All right, let's go on to the next one. Let's say C2H3O2. This is acetate. And we'll say it's acetic acid. Strong or weak? I would say this is a middle ground electrolyte. Okay, if we're thinking about it on a spectrum between strong and weak, I think it'd be around right here. Okay, because it is an acid. Now, if we just put acetate in there, this I do not believe would break up, right? It is just bonds between carbons, hydrogens, and oxygens. So I don't think that it would break up into anything substantial. And that would mean it would be a weak electrolyte. I'm not going to write electrolyte because I didn't up above. All nonmetals. So it's most likely not going to break up in water. It's not going to dissolute in water. However, I'm going to throw a tricky one at you. Strong or weak? I would call this one a strong electrolyte. Okay, because the tricky part is NH4 is a polyatomic ion that is charged. Okay, it's NH4 plus, meaning that it can break apart into Cl minus and NH4 plus. Okay, so it may be all nonmetals, but it has a polyatomic ion in it. So while this can be a useful tool for you guys to use in the general sense, especially when dealing with things that contain carbon, it is not always going to be correct. Okay. Lastly, there's one more thing I wanted to say. I can't remember, so we'll just put it in another video if we need to. So, one last one. Let's say, I remember now. Let's do Na3PO4. Okay. This would also be a strong electrolyte. Okay, it is a sodium salt, so it's a sodium salt, so it will be soluble. Okay, also, let's look at the number of things it's going to break up in. It's going to form 3 Na pluses and 1 PO4 minus. Okay, that is a total of 4 charged entities, we'll say. Not atoms, because this isn't an atom. But 3 charged entities. Or 4 charged entities. Say that 5 times fast. 4 charged entities, 4 charged entities, 4 charged entities. Whew. But if it's breaking up into multiple different entities, 4, 5, 6, anything above that, then it is highly strong. Okay, that means there's more charge in the solution, and that means that it is more susceptible to electrical input. Okay, so that was a lot of information I just threw at you guys. Okay, go back through the video, watch it maybe one or two times. It's not because I want my views up. It's really just so you guys can understand the information. It's a lot to be put out there in a 20-minute span, but due to all this coronavirus stuff, it's something we have to do. So you guys have time if you want. Watch it, take notes again, and make sure you didn't miss anything. Okay? Stay healthy, and I'll see you guys on the next video.